Hello, my name is Wishuwinap Krambun from Bangkok Christian College. Today, I will be presenting my report for problem 13, Singing Ruler. The problem states that when a ruler is clamped at one end and struck, it oscillates and emits a characteristic sound. Investigate how the sound depends on relevant parameters. The ruler is rigidly clamped to a table using a C-clamp. Excitation is a light reproducible finger tap at the free end. Sound is recorded using the Feedfox app on a smartphone placed close to the tip. Data are exported and processed in Google Colab with Python to create a turntable. The clamp ruler is modeled as a cantilever beam. Obeying the Euler-Bernoulli equation, we know that the density is equal to the mass over volume, and volume is equal to the cross-sectional area times the length. After rephrasing, we can see that m is equal to rho al. After applying the equation mentioned, we can see that f is equal to square root of 3 divided by 2 pi l squared times the square root of EI over rho A. Is the area moment of inertia theory. Factor 1, overhanging length. Thickness at 4 millimeters and the width at 1 centimeter were held constant. The overhanging length tested were 5, 7.5, 10, 12.5, and 15 centimeters relatively. According to Bernoulli's equation, f equal 1 over 2 pi times the square root of 3 EI over ml cubed, we can extract 1 over L squared and assume that the square root of 3 over 2 pi times square root of EI over rho A is a constant number, so we can see that the natural frequency is inversely proportional with L squared. These are graphs made from Excel application. In the x-axis is the hanging length in centimeter, and for the y-axis is the average frequency in hertz. For example, at 5 centimeters, the average frequency was 2,644.21 hertz. And for 15 centimeters, the average frequency was 932.7 Hz. In conclusion, for the first factor, it is clear that the greater the overhanging length, the lower the average frequency becomes. This directly confirms the theoretical prediction: the natural frequency is inversely proportional to the overhanging length. Factor 2, ruler's thickness. In the series, the independent variable was the beam thickness h. The control variables were strictly maintained as 1. The free overhang length, which is 10 centimeters, and 2. Cross-sectional width at 1 centimeters. Applying the area moment of inertia into Bernoulli's equation, we get f equals to square root of 3 over 2 pi l squared times the square root of EBH cubed over 12 rho A. And after rephrasing, we can see that the other variables except for h to the power of 1.5 is a constant number, making the natural frequency proportional with h to the power of 1.5. These plotted data reveal fundamental frequency in hertz versus thickness in millimeters. For instance, for millimeters thickness, the measured fundamental frequency is 2054.69 hertz. And for 1 millimeter the least, we have 422.3 hertz. With fixed 10 centimeter overhang, the fundamental frequency rises from 422 Hz at 1 millimeters to 2563 Hz at 5 millimeters thickness. The correlation coefficient R squared is equal to 0.9, confirms that the natural frequency scales precisely as thickness to the power of 1.5, exactly as predicted by Euler-Bernoulli theory. So, the term that the natural frequency depends on h to the power of 1.5 is experimentally verified. Factor 3, cross-sectional area A, 1, 2, 3, 4, and 5. We kept the overhanging length at 10 centimeters and the thickness at 4 millimeters constant, and varied only the width of the ruler. Theory predicts that when L and H are fixed, the fundamental frequency must scale as F inversely proportional with A to the power of negative 0.5, because the stiffness EI increases linearly with width, while the mass per unit length rho A also increases linearly. Our measured frequencies drop from about 1900 at the smallest area to 553 Hz at the largest. Plotting frequency against A to the power of 3.5 yields a perfect curved line, with R squared is equal to 0.9, fully confirming the theoretical scaling that natural frequency inversely proportional with square root of A. In conclusion, all experiments confirm Euler's Bernoulli theory. Thank you.